Okay, welcome to our Best Out of 5 project. This project is interesting because it's based on the foundations of statistics, and in fact from reading the book The Unfinished Game by Keith Devlin. Keith Devlin is also the first person that they interview in the documentary, the Nova documentary Prediction by the Numbers, so you will have seen him in that documentary as well. The Unfinished Game is a very low-level math book. It's kind of fun, and it talks primarily about the issue of determining what happens when a game like Best Out of 5 is interrupted. So interrupted meaning that the game has to stop, but you still know something about the game. So in this case, a game of Best Out of 5 is interrupted when player A has won twice and player B has won once. The game ends when a player wins 3 times. So player A's really close to winning, player B is not as close to winning. And there's lots of ways of getting this wrong. So the way I'm going to introduce this initially is what's called stochastic modeling in mathematics, or in physics would be called the Monte Carlo method, and in other disciplines probably has other names. Basically, we're going to see what happens when we do this many, many times. So I'm asking you to actually finish this game 100 times. So take out a piece of paper, write game number 1, round number 4, round number 5, and then figure out who wins. So when you flip a coin, let's decide that A wins if you flip heads and B wins if you flip tails. So in this example that I give, the first game, player A wins, round 4. So that means I flipped heads. And that, of course, means that player A has won. Player A has already won twice. This is the 3rd time. So therefore, player A wins that game. We're going to do this 100 times. So, for example, maybe the 100th game looks like this. I flipped a tail for round 4. That means it's now tied. A and B both have 2 wins. And then in round 5, I flipped tails again, which means that B now has 3 wins, and so B wins the game. So actually go through and do that. Now there's other ways of doing this. So one of the things that I did is I actually created a spreadsheet. So let me show that as a spreadsheet file. And I used a random seed to determine who won each round. And then, of course, the correct number of wins gave me who won the entire round. And then I counted up each time that player B won. So, for example, here, it looks like in game 5, player B won, in game 6, player B won, and so on. And then I continued in this way. As I'm scrolling down, you can see I did this 100 times, and I got that player B won 27 times. So this is a nice way of using computers to model statistical things. This is such a simple situation that a spreadsheet works really well for it. If you want a free open source application that does this in a much more sophisticated way, you can run millions of experiments, you can have all sorts of contingencies. Octave is a perfect choice for that. In fact, I've been doing some Octave simulations this summer, which is kind of cool. So back to our game. Player A won how many of these games? Well, player A won 73. Remember, B won 27. So what would the probability that player A wins the game be? 73%. What's the how many games did player B win? That was the 27 from our simulation. And what's the probability that B would have won the game had they continued playing? Well, remember there was 100 games, 27 out of 100 is 27%. Now, just like anything that is playing off the law of large numbers, 100 isn't really that big. And there are other issues. 27 is not exactly the theoretical answer, and so let's look at why it's not. So on the next page we say a student created the following table. This isn't just students. Remember, Blaise Pascal and Pierre de Fermat were engaged in this exact same discussion. So there they are. Fermat is interesting for many reasons. Fermat's last theorem, for example, and Blaise Pascal is interesting in my world because he actually is the first person to have gotten a patent for the idea of transit. That is, fixed routes, fixed schedules, fixed fares for the same for everyone, and running at a fixed timetable. So, interesting connection to our modern world. So, this is one of the things that those two at the beginning of statistics considered, and that was what would happen if player A won round 4. So take a look at that. Here is a very credible looking table. In rounds 1, 2, 3, A won twice, B won once, so we're in the same situation as on the previous page. And you might say, the moment that A wins round 4, A has won the game. I mean, there's no point in playing round 5 at that point because A has won. Now, I certainly agree with that. There's nothing wrong with that line of reasoning. The problem is when you focus on the unfinished game aspect of this, then you have a kind of ludicrous situation going on here. So let's talk about this in two ways. One is, if you look at the Socratic model on the previous page, and granted it was only 100 throws, B won about 27% of the time. This says, theoretically, B should win about 33.3% of the time. And that's not an insignificant difference. That's pretty large, the difference between approximately a quarter and approximately a third. And similarly, this theoretical model says that A should win 2/3 of the time. Well, we got closer to 3/4 of the time when we did this with the computer model. So something's looking weird already. And then something looks even weirder. So the next question is, why is this wrong? So I think from the previous page we know that it's wrong. Now, this is a new style of statistics, the idea of performing experiments and seeing what the results are. Now, unfortunately, if you really do this 100 times, your number of successes for B could be pretty close to 1/3. 100 isn't that big. But with a computer, you can do this 1,000 times, 1,000,000 times. I often run simulations 1,000,000 times, and on a fairly fast computer, that will take less than 15 minutes. So we can do a lot now that we couldn't do then. But I want to focus your attention on round 4. Remember, the assumption in statistics is that each of these outcomes is equally likely, and that certainly is what we'd expect from a fair coin. We'd expect A to win half the time and B to win half the time. But already in round 4, we can see that something really wonky is happening. It looks like we've divided round 4 into 3 cases where B wins twice and A wins only once. We're basically saying that B wins twice as often as A in round 4. So that's the way I'm going to address this issue. I'm going to say that this table assumes that B wins round 4 2/3 of the time. In fact, for a fair coin, A should win as often as B. So one of the ways you can look at this is just looking at a single round and saying, well, there's no way that B wins twice as often as A if this is a fair coin. The next table asks us to make show what the true probabilities would look like. So let's quickly go through and do that. The first thing that I would point out is that in round 4, A should be as likely to win as B. Now, when we see that each of these rounds then has another round after it, you can see why I divided this into 4 pieces. 2 squared, if we had 3 more rounds, it might be 8 pieces. 2 cubed, right? Half of a half, and then half of a half of a half. So we're dividing this into fourths. We're saying in 2 of those cases, A wins, and in 2 of those cases, B wins. So round 4, without looking at anything else, looks good to me. There are as many cases where A wins that particular round as B winning that particular round. Now, you might say, well, what are we going to say about round 5 if A has already won in round 4? So let's talk about that. So in round 5, you might say A has already won. You might say, why even toss the coin again? A has won. Now, I'm going to show this in a kind of branching tree model so that we can see each of the 4 possibilities. And I'm going to say, well, maybe we played another hand even so. we toss the coin again. A won in round 5, and of course that means, well, A's already won, but now won by one more. If in round 5 B wins, well, remember A's already won, so that hasn't changed anything. So you might say, what's the point of talking about round 5 at all in this case? And I claim that the point is to show that A and B are still equally likely, and in those two cases, regardless of what happens in round 5, A still wins. Now, what if B wins round 4? Well, we've already talked about the fact that it should win as often as A. So let's see what could happen in round 5. Well, A could win again. A still could win, because if B wins round 4, it's only 2-2. B's won 2, A's won 2. A can still win the game if A wins round 5, and that's exactly what happened in this case. Now, in all 3 of these cases, A has won. And so we can see that there are 3 cases in which A is winning. So we can see that the numerator is 3. Similarly, right at the beginning when we saw that this was going to be broken in half twice, we knew that we were going to have fourths. So that gives us our 3/4. So there's the 3/4, the 75% chance that A wins. Now there's one more case, and that case is when B wins round 4 and B wins round 5. Now that certainly can happen, but it only happens 1/4 of the time. And when that happens, that's the only way in which B can win. And just like 3/4 is the probability that A wins, the remaining probability, 1/4, is the probability that B wins. So now it asks, what is the probability that player B would have won had they continued to play? And I'm going to say the probability that player B wins is 1/4. An interesting look at the beginning of statistics, and an interesting look at some of the misconceptions that had to be overcome for statistics to work for these fairly simple problems. I hope you enjoyed that.